Hello my friends and welcome back to the Today Machine channel. The raw material, consisting of many individual wires of varying thicknesses, arrives on coils. Each wire is first tested for strength to ensure the final rope meets the required load-bearing capacity. Once the wires pass inspection, they are transferred onto spools. These spools are then placed in a stranding machine. The process starts with pulling the wires through the stranding head, where they are twisted together to form the first strand. During this process, the rope is lubricated with grease for protection. The stranding machine's basket rotates while simultaneously pulling the wires, resulting in a tightly wound strand. Multiple strands are twisted together to form a complete wire rope. Regular checks are performed throughout production to ensure the rope's diameter meets specifications, either manually or using a laser measuring device. A final tension test is conducted to verify the rope's strength and safety. The finished rope is wound onto large spools, or bobbins, which can be up to 5 meters high. These bobbins, sometimes weighing up to 150 tons, are loaded onto trucks using specialized cranes and transported to the customer with escort vehicles to ensure safe delivery. The profession of hand splicing wire ropes is an ancient and rare craft that requires immense skill, patience, and physical strength. Even in modern times, where machines handle most tasks, some specialized jobs still rely on traditional handwork, such as splicing a 72 mm diameter wire rope. This specific task is one of the hardest forms of manual labor, demanding precise technique and brute force to manipulate heavy and rigid wire strands. Wire rope splicing involves intertwining the strands of the rope to create loops or eyes, often used for lifting and securing loads. In the case of a 72 mm wire rope, the process becomes significantly more complex due to the size, weight, and resistance of the rope material. The splicer must be experienced, as the wire strands can be sharp and unforgiving if not handled properly. First, the individual rope strands are carefully unraveled and separated. Then, using a combination of tools like marlin spikes and mallets, the splicer interweaves these strands back into the rope's structure, ensuring a tight and secure splice. This process can take hours, depending on the length and complexity of the splice required. The physical toll of hand splicing a 72 mm rope cannot be overstated. The size of the rope means it's incredibly heavy and difficult to manage, requiring the splicer to exert considerable force just to move and manipulate it. Furthermore, the repetitive nature of the work, combined with the precision required, makes it not only labor-intensive but mentally taxing as well. Despite the challenges, hand splicing remains irreplaceable in certain industries, especially where custom lengths or specific rope configurations are required. For example, in offshore and marine environments, large diameter ropes are often used for mooring or heavy lifting, and a secure, well-made splice can make the difference between a successful operation and a catastrophic failure. This craft, though rare, ensures the longevity and safety of such operations. In a world increasingly dominated by automated solutions, hand splicing stands out as a testament to human ingenuity and strength, preserving an essential skill that continues to be valued in critical, heavy-duty applications.
The wire rope sling market is poised for substantial growth due to increasing demand across various industries like construction, mining, shipping, and oil and gas. In 2023, the global wire rope sling market size was valued at approximately $1.5 billion and is projected to grow at a compound annual growth rate (CAGR) of 5.8% from 2023 to 2030. This growth is driven by the need for durable lifting equipment capable of handling heavy loads in demanding environments. Wire rope slings offer high strength, flexibility, and resistance to abrasion, making them ideal for industrial applications. The construction industry, accounting for over 30% of the market demand, is a major driver, with ongoing infrastructure development projects across North America, Europe, and the Asia-Pacific region. Moreover, increased investments in renewable energy, particularly offshore wind farms, have boosted the demand for wire rope slings, as they play a crucial role in transporting and installing large components like turbines and foundations. Regionally, Asia-Pacific dominates the market with a market share of around 40%, thanks to rapid urbanization and industrialization in countries like China and India. North America is another key market, driven by a strong mining and oil and gas sector. Technological advancements such as the use of galvanized and stainless steel materials, which offer superior corrosion resistance, are further supporting market growth. The competitive landscape of the wire rope sling industry includes companies focusing on product innovation, quality improvement, and service offerings. Leading manufacturers are also expanding their global presence through mergers, acquisitions, and partnerships to tap into emerging markets. The demand for custom solutions tailored to specific lifting requirements is also on the rise, offering further market potential. The synthetic slings market, though smaller compared to wire rope slings, is experiencing notable growth due to the increasing preference for lightweight and flexible lifting solutions. In 2023, the synthetic sling market was valued at approximately $0.8 billion and is projected to grow at a CAGR of 6.2% from 2023 to 2030. Synthetic slings, typically made from materials like nylon or polyester, offer advantages such as ease of handling, resistance to moisture, and non-conductivity, making them suitable for delicate or lightweight lifting tasks. The market is expanding due to their adoption in sectors such as aerospace, logistics, and manufacturing, where precision and gentler handling of cargo are required. The Asia-Pacific region leads the market, accounting for around 45% of the global demand, followed by Europe and North America. Innovations like high-performance synthetic fibers are further enhancing their load-bearing capabilities, making synthetic slings a more viable alternative to traditional steel slings in specific applications. With growing emphasis on safety and efficiency, the synthetic sling market is expected to witness steady growth in the coming years, driven by industries seeking safer and more efficient lifting solutions. The wire, rope, and sling testing services market is essential for ensuring the safety, performance, and compliance of lifting equipment across various industries. With increasing industrial safety regulations, the demand for these services is witnessing significant growth. In 2023, the global market for wire, rope, and sling testing services was valued at $450 million and is expected to grow at a CAGR of 6.5% until 2030. Testing services encompass load testing, visual inspection, and non-destructive testing, NDT, to assess the structural integrity of slings, ropes, and related lifting equipment. The rise in workplace safety awareness, especially in sectors like construction, oil and gas, and manufacturing, has heightened the need for periodic testing to avoid potential hazards and costly equipment failures. North America and Europe are the leading regions in testing services, accounting for over 50% of the total market due to stringent safety regulations and a higher concentration of industrial players. However, the Asia-Pacific region is projected to grow rapidly, driven by increasing investments in infrastructure and industrial projects in countries like China, India, and Japan. Market players are focusing on offering advanced testing solutions, such as automated testing systems and cloud-based data management, which provide real-time monitoring and reporting. As industries continue to prioritize safety and regulatory compliance, the testing services market is likely to witness sustained growth, offering significant opportunities for specialized service providers. The fiber rope market, comprising natural and synthetic ropes, is expanding rapidly due to the growing demand in sectors like maritime, sports, industrial, and defense. In 2023, the global fiber rope market was valued at $2.1 billion and is expected to grow at a CAGR of 5.4% from 2023 to 2030. The increasing shift towards synthetic fiber ropes, driven by their superior strength-to-weight ratio and resistance to environmental factors, is a key factor behind this growth. Synthetic ropes, such as those made from high-modulus polyethylene, HMPE, polyester, and nylon, are becoming more popular in maritime applications for mooring, towing, and anchoring due to their durability, lighter weight, and ease of handling compared to traditional steel wire ropes. The oil and gas industry is another significant end user, with fiber ropes playing a crucial role in offshore operations, where they are used for riser tensioning, lifting, and other subsea applications. The sports and recreation sector is also contributing to market growth, with fiber ropes being used in activities like climbing, sailing, and water sports. In defense, fiber ropes are employed for applications like aircraft arresting systems and military cargo lifting, due to their strength and reliability. Geographically, North America and Europe dominate the fiber rope market, holding a combined market share of over 55%, driven by their robust maritime, defense, and industrial sectors. The Asia-Pacific region, however, is projected to experience the highest growth, fueled by rapid industrialization and increased maritime activities. As industries continue to recognize the benefits of fiber ropes, including longer lifespan and enhanced performance in harsh conditions, the market is expected to witness consistent expansion, with new applications and innovations further driving demand. Eyebolts, known for their circular loop at one end and a threaded shank at the other, require exceptional strength and resilience. Closed die forging ensures that these requirements are met by producing eyebolts with improved grain flow and mechanical properties. The process begins with the selection of the appropriate raw material. The next step involves cutting the raw steel into billets, which are small cylindrical pieces. These billets are then heated to high temperatures, typically between 1100 degrees Celsius and 1250 degrees Celsius, 2012 degrees Fahrenheit to 2282 degrees Fahrenheit, depending on the type of material. This heating process is critical as it softens the metal, making it more malleable and easier to shape during the forging process. Closed die forging requires the use of a pair of custom-designed dies, one for the top and the other for the bottom. These dies contain the impression of the final eye bolt shape. The dies are made from high-strength materials, such as tool steel, that can withstand extreme pressure and temperature. Before the forging process begins, the dies are preheated to prevent rapid cooling of the metal and ensure a consistent finish. In the closed die forging process, the heated billet is placed between the two preheated dies. A forging press or hammer then applies immense pressure, causing the billet to take the shape of the die cavity. This process is done in several stages. Initial forging. The billet is roughly formed into the shape of the eye bolt. Intermediate forging. The shape is refined to approximate the final product. Final forging. The metal flows completely into the die cavities, creating the precise dimensions and features of the eye bolt. The closed die forging process ensures minimal material waste and a near-net shape product, meaning little post-forging machining is required. After forging, excess material, called flash, often forms at the parting line where the two dies meet. The eye bolt is trimmed to remove this flash and create a smooth, clean edge. Trimming is typically done in a specialized trimming press. Once the eye bolt is forged and trimmed, the shank, the straight portion, undergoes a threading process. This is done by rolling or cutting threads onto the shank. Rolling is often preferred as it improves the material's fatigue strength by cold working the surface. To achieve the required mechanical properties, the eye bolt may undergo a heat treatment process, such as quenching and tempering. This step increases the bolt's hardness, tensile strength, and resistance to wear. It also ensures the eye bolt can withstand heavy loads without deforming or breaking. After heat treatment, the eye bolts are usually cleaned and may undergo surface treatments like galvanization or zinc plating to improve corrosion resistance. In some cases, black oxide or passivation treatments are used for stainless steel eye bolts. The final step is a rigorous quality inspection. The mesh gabion weaving machine operates with a system of interconnected components. The crankshaft and connecting rods work together to drive the internal gear sets, which power the machine's movement. A pendulum mechanism moves back and forth, reversing the direction of the twisted wires. The mesh is formed by a double twisting process, creating hexagonal openings as the wires are twisted around each other. A rotating shaft, powered by a 22 kVA motor controlled by a cone shaft, feeds the wires. This shaft, called the spike shaft, aligns the wire spikes 6 cm apart horizontally and 8 cm vertically. The wire is then twisted into multiple layers inside a hollow tube. A fully automatic chain link fence making machine streamlines the production of chain link fences by automatically weaving wire into a mesh. The process begins by feeding galvanized wire from spools into the machine's straightening and cutting unit. This ensures the wire is uniform and ready for the weaving process. Once the wire is cut to the required lengths, the machine twists the wire to form individual chain link, knuckles, or loops. The machine's core mechanism involves a rotating spindle that weaves the wire in a zigzag pattern to form a continuous diamond-shaped mesh. This mesh is formed by intertwining adjacent wires to create a flexible but sturdy fence. After the mesh is woven, the machine cuts it to the desired length. It can also crimp the edges, reinforcing the mesh and ensuring it stays intact. For increased efficiency, some machines have a built-in system for rolling up the finished mesh, which can then be easily transported or stored. Advanced models can adjust the size of the mesh openings, wire thickness, and fence height automatically, making the machine highly versatile. These machines significantly reduce manual labor and increase production speed, making them ideal for large-scale fencing production. Additionally, with user-friendly controls, operators can manage production with minimal effort. Manual chain link fence making is an ideal business for self-employed individuals due to its low startup costs, minimal space requirements, and reduced power consumption. In a small-scale manufacturing unit, the process involves manually feeding galvanized wire into a simple weaving jig. The operator twists and interlocks the wires to create the diamond-shaped mesh pattern characteristic of chain link fences. This method requires basic tools, such as wire cutters, pliers, and manual weaving frames. The finished mesh is cut to size, crimped at the edges for stability, and rolled up for sale or installation. Because this process consumes less power and can be done in a compact workspace, it's ideal for small-scale entrepreneurs looking to start with minimal investment while serving local markets. Wire rope splicing is an intricate and labor-intensive task, particularly when dealing with larger diameters like 1.5-inch wire rope. Splicing involves joining two ends of a rope or creating an eye by interweaving the rope strands back into itself. In the context of wire ropes, the splicing process is often employed to create loops for lifting, rigging, or securing purposes. This technique is crucial in industries such as maritime, construction, and heavy lifting, where reliability and safety are paramount. The splicing process. Splicing a 1.5-inch wire rope is a physically demanding and technically challenging process. The first step involves unraveling the individual strands that make up the wire rope, typically 6 or more, depending on the rope's construction. Each strand must be carefully separated, which can be difficult due to the rigidity and strength of the wire material. This is typically done using specialized tools like a marlin spike, which helps to open the lay of the rope. Once the strands are separated, the splicer then begins the process of weaving them back into the body of the rope. This process is known as tucking, where the strands are fed in a specific sequence to ensure a tight, secure splice. The goal is to make the splice as strong as the original rope, ensuring it can withstand the same loads and stresses. The process requires precision and experience, as improper tucking can weaken the rope and lead to failure. Challenges in splicing large diameter wire rope. Working with 1.5-inch wire rope presents several unique challenges. The size and weight of the rope itself are significant factors, as even short lengths can be cumbersome to handle. The splicer must often work in awkward positions, applying considerable force to manipulate the stiff wire strands into place. Additionally, the process can take hours, depending on the complexity of the splice and the environment in which the splicing is performed. Safety is a major concern when splicing wire ropes of this size. The strands of wire are sharp and can cause serious injury if not handled correctly. Protective gloves and clothing are essential, but even with precautions, the risk of cuts, punctures, and fatigue-related accidents remains high. The repetitive nature of the work, combined with the physical effort required, makes this one of the most demanding jobs in the field. Applications of wire rope splicing. Despite advances in technology, wire rope splicing continues to be an essential skill, especially in industries where custom solutions are required. For example, in the offshore oil industry, large wire ropes are used for mooring ships or securing oil rigs. The splices in these ropes must be flawless, as a failure could lead to catastrophic consequences. Similarly, in construction, wire ropes are used for crane operations and lifting heavy loads, where spliced eyes are used to connect to hooks or other hardware. The durability and strength of a well-spliced wire rope make it indispensable for these high-stakes applications. While mechanical splicing methods exist, they are not always feasible for large-diameter ropes or custom-length applications, ensuring that the traditional method of hand splicing remains relevant even today. Rope and webbing slings play a crucial role in industry and construction by securely suspending, tying down, or supporting heavy loads during lifting operations. Understanding how these slings are manufactured can provide insight into the importance of precision and strength in their production. A visit to Exer plant in Bielsko-Biala reveals the meticulous process involved in making polyester slings and belts, as well as steel rope and chain slings. The production of polyester slings begins in the sewing room, where high-strength polyester tape arrives and is automatically cut to specific lengths. The widest tapes, capable of handling loads up to 20 tons, are 300 millimeters wide. Special sewing machines give the slings their final shape. Each sling undergoes rigorous safety measures, with a safety factor of 7:1, meaning a sling designed to hold 1 ton must withstand a breaking test at 7 tons. Endless slings, another polyester-based product, are named for their continuous loop shape. Made from a core of polyester fibers wrapped in a durable sleeve, the slings are woven and stitched on specialized machines. The final product is sewn with a label and sealed in protective foil, ready for shipment. An automated line produces a 2 closed-circuit polyester belt slings, primarily used in industries such as metalworking and construction. These single-use slings, capable of lifting up to 2 tons, pass through an ironing machine, are cut to size, and sewn together with information labels. The line can produce between 600 and 1,200 slings per shift, in varying sizes from 23 to 63 millimeters wide and 50 centimeters to 5 meters long. In addition to polyester slings, this plant manufactures metal rope slings. These slings start with steel rope cut to length, which is then looped and secured with an aluminum sleeve crimped under 1,500 tons of pressure. The rope ends are thermally processed to prevent unraveling, ensuring durability in lifting capacities exceeding 50 tons. Chain slings, used for similar heavy-duty applications, are manually assembled from chain links, connecting components, and hooks. Once the slings are assembled, they undergo extensive testing to ensure safety. A horizontal tension test bench stretches each sling until it breaks, verifying that they meet stringent safety standards. These tests guarantee that slings will perform safely and reliably in their intended applications. Forging chain anchor shanks, especially using 4140 steel, involves a complex and highly precise process due to the material's strength and resilience. In this case, the forging takes place on a 500-weight Massey hammer, a type of drop hammer known for its robustness and precision in heavy-duty forging applications. The process starts with the first heat, where the raw material, typically 140 millimeters in diameter, is heated to a forging temperature, around 900 to 1200 degrees Celsius for 4140 steel. In this initial stage, the aim is to slab the stock, which means reducing the diameter and shaping the material into a more manageable and elongated form, preparing it for the next stage of shaping. This first heat is crucial for establishing the rough dimensions of the anchor bolt, ensuring the steel's grain structure is refined and ready for further deformation. The second heat is where the actual shaping of the shank occurs. Once the slabbed material is reheated, the 23 kilograms forging is shaped under the 500-weight Massey hammer. The repeated strikes of the hammer compress the steel, aligning its grain structure along the length of the shank, which enhances its strength and durability, critical for chain anchors that must withstand enormous stresses in their final application. Forging at this stage focuses on creating the final dimensions of the shank, including the anchor bolt's head, which might be drawn out or upset depending on design specifications. The use of 4140 steel, known for its excellent toughness, good hardenability, and resistance to fatigue, makes it ideal for anchor bolts, ensuring long-term performance in harsh conditions.